Hello, folks. So, we are back talking about an ice skating rink problem. I want to do a quick worked example to kind of just illustrate what we're talking about when we're saying that we're conserving momentum. So, the problem reads for us that we have two ice skaters that are at rest in the middle of a 20-meter diameter ice rink. At t equals 0 seconds, the skaters push off of one another. So I have two skaters here. The 55 kilogram skater reaches the wall after pushing off of the other skater at 6.67 seconds. When does the 80 kilogram skater reach their side of the wall? So we have a brief illustration of what's going on here. I have two folks kind of just in the center of this rink. I know that the radius of this rink is 10 meters. We gave you the diameter as 20. Tricky. And we know something about how long it takes skater 1, let's call them, to reach the wall. And so we can kind of just right off the bat say V1 is going to be 10 meters over 6.67 seconds, right? So that starts to give us a little bit of a velocity here. 10 divided by 6.67, right? We are going to get roughly 1.5, right? And that makes sense. I have 2/3 here. So cool. All right. Now, so that was kind of background information. This was information setting up the problem. Now we actually need to start the problem. We need to start by asking a fundamental question, the same fundamental question that we started asking ourselves back in chapter 10. Is this an isolated... Ooh. What happened there? Isolated problem. Is this an isolated situation? System. Is this an isolated system? Are there outside forces working on this, doing impulses? I would say no. We're not really interacting with the ground very much. We've taken friction out of this system. So really the only collision is between these two people. And it's almost like an explosion. I start off with one unified system that breaks up into two parts. So I would say yes. Yes, it is isolated. So delta P has to be conserved. Or P needs to be conserved. Delta P equals 0, right? And we're only thinking in one dimension here. Even though this is a circle, we're not adding two dimensions into this. We're saying they push off of each other and they move in straight lines. So that straight line, we're just going to say delta px equals 0, right? Pxi equals pxf is how we're going to talk about it. Now, what momenta do we have to begin with? Well, I don't think we have any momentum, right? Both skaters are at rest. We're actually told that in the problem. And so if I even were to draw this out, m1 v1 I plus m2 v2 I, both of these velocities would go to 0. And so I'm left with 0 on the left-hand side. On the right-hand side, I have m1 v1 f plus m2 v2 f. So this is basically what we're working with here. And I want to say something about v2f so that way I can talk about how long it takes for this skater to actually reach their side of the wall. So if I have negative m1 v1 on one side equals m2 v2, I'm going to drop the f's for right now, but they are the final velocities of our problem here, and divide by m2 on both sides. M2 just erase this. Then I have an expression for V2, right? So V2 is going to be negative 55 kilograms times 1.5 meters per second divided by 80 kilograms. So plugging that into your calculator, negative 55 times 1.5 divided by 80. I get roughly, within rounding error, negative 1.0. So negative 1 meter per second. If we're really taking it out to a couple decimal places, I get negative 1.03. But I think 1 meter per second is perfectly fine. And it's negative. We're showing a directional aspect here. So I've actually said that V1, if we take V1 to be positive, which is normally to the right, but here I've kind of said to the left, then to the right is positive, right? If to the left is positive, sorry. I think I messed that up. If to the left is positive, to the right is now negative. And that's what we're showing with this negative 1 meter per second. So the last bit, how much time does it take for this 80 kilogram skater to reach their side of the wall? Well, they are going 10 meters, right? They're going the radius of this circle divided by negative, well, not negative, 1 meter per second, right? We can't have a negative time here, so we're going to take an absolute value. And we find out that it's 10 seconds. It takes 10 seconds for the 80 kilogram skater to reach their side of the wall. It takes 6.67 seconds for the first one to reach their side of the wall. So this is how momentum can help us figure out complicated interactions like this. Notice we didn't actually talk about anything about the forces exchanged, but we know that the forces exchanged between them have to be opposite and equal. That actually is enough information to give us the rest of the problem. So that was an example problem of conservation of momentum in an isolated system. Next lecture is going to be about the different types of collisions. So if you have a question about this, come see me in an office hour or shoot me an email. All right? Have a good one.